All right, here we are on December 8th. We are going to do a lesson here on 3.8 inverse trigonometric functions and their derivatives. I have a small contingent of amazing students here. Hello, everyone. And we're going to start with homework questions from 3.7. Does anybody have a question from 3.7 they'd like to look at, right? Let's do it. So we've got product rule in there. We've got x squared times y. Let me get my pen working. X squared times y minus x times y squared equals 4, and we're to find when the slope of the curve is defined. All right. So if I want the slope of the curve, my target is dy dx, and they want to know when it's defined. So I think I'm going to be figuring out the points of discontinuity, and hence where the function is not differentiable. And the tangent line would likely be vertical or something like that. I could graph this in Desmos to get a good idea too of where we think it could be undefined, but maybe we'll do that, maybe not. Let's go ahead and do the implicit differentiation. So I'm going to differentiate the first term. It is a product, so I'm going to write down I'm thinking of my u as the x squared and my v as the y. So I have x squared times the derivative of y, which is y prime, plus y times derivative of x squared, which is 2x. So that's the derivative of my first term. Minus, and now we're going to differentiate our second term implicitly. Again, it's a product, so I'm going to put a parentheses here because of that minus sign. And then let's think it through here. So it's going to be x times the derivative of y squared. So the derivative of y squared with respect to x is 2y times y prime by the chain rule, plus y squared times the derivative of x, which is 1. This is supposed to be equal to, and watch out, common error here. A lot of people forget to differentiate the right side, and they just write down 4. It's easy to do. But remember, we're differentiating 4, and so the derivative of a constant is 0. All right. Any questions up to this point? Okay. So big product rule problem, which is great because I did grade those quizzes. They're gonna go in Canvas, and product rule. Woo, we missed that big time on the quiz. That's a conversation for when more of you are here. All right. So remember, the target in this whole thing is to isolate dy dx because we're trying to figure out something to do with our slope. So I'm going to try and isolate my y prime. First, I should probably get rid of those parentheses. So I have x squared y prime plus 2xy, I suppose, would be how I would rearrange that, minus 2xy y prime minus y squared. This equals 0. Next, I'll move all the terms that do not have y prime to the other side. Wait, I feel like I'm missing a prime. There we go, right there, yeah? I don't think my stylus wrote it. All right, so keeping the terms that have the primes, I get x squared y prime minus 2xy times y prime equal to, so here I'm going to subtract the 2xy, and I'm going to add the y squared. So I get y squared minus 2xy. Factoring out y prime, I get y prime times the quantity x squared minus 2xy. is equal to y squared minus 2xy. This is kind of interesting. If I divide through by my coefficient, I get y prime is equal to y squared minus 2xy over x squared minus 2xy. So there you have it. We've defined y prime in terms of y and x only. Any questions up to this point of the problem? Yeah. Let me grab a highlighter. Highlight. Let's see. I got to go up one more, don't I? Or do I? So when I differentiated that y, I ended up getting a y prime there. And when I differentiated this y squared, I ended up getting that 2y y prime there. So that's kind of where they came in. Does that make sense? Any other questions on this so far on this problem and defining y prime in terms of x and y? Okay. So to answer the question in the problem, they wanted to know when is this function undefined? And I think we're going to get a pretty sophisticated response to this because take a look at that denominator. One of the things that would cause an issue for our function, our derivative, is if the denominator were equal to 0. We cannot divide by 0. And so my derivative, it will certainly be undefined if the denominator equals 0. So I'm gonna set the denominator x squared minus 2x times y to not be equal to 0. So let's go ahead and define this in terms that we might understand more simply. So I'm going to add the 2xy to the right, dividing through by 2x. I get y is equal to x squared divided by 2x. Oh, these were not equals, weren't they? That does simplify, but it immediately throws a caution to my mind, like can x equal 0? Since I've got this x in the denominator there, I'm thinking x can't equal 0, and then we get the line y equals or cannot be equal to x over 2. So I'm really curious about this one. I want to see if that is somehow accurate, and it's going to take some work in Desmos to check exactly what's going on here. Did we also see in the answer in the text? Does that agree with what's in the text for restrictions on where it can be differentiated? Or y equals x over 2. So it is correct, but it's one thing to be correct. It's another thing to actually like get what's going on here. So let's try and visualize this in Desmos. It's kind of fun to do this because these expressions are all, I think, pretty new to us. We haven't done a lot of work with these types of equations, so it's fun to see what they look like. So here's x squared times y minus x times y squared. I got a capital Y, I don't know why. This is supposed to be equal to 4. So it's really fascinating. This is not actually a hyperbola. This is something else. I don't think it has a name that I know of. It's not like a classic family of functions. But it's cool looking. I'll say that. And then something I can do to visualize the derivative, it's a little bit convoluted, but I can add a point with sliders, and this point can freely move, and then I can define the tangent line of the function. This is only if I know the variable. So, sorry, only if I know the derivative. We solved for dy dx earlier. So let me put that in here as a function defined in terms of x and y. And it's y squared minus 2xy over x squared minus 2xy. So that was our derivative. And the thing is, Desmos can't graph it. It's not able to do that. That would be really sophisticated. What I can do instead is I can define a line, a tangent line, for this blue point as I move it freely along space. So let me see if I get this right. It would be the y value, which is f of a comma b. Y value of the derivative is the slope. Oh gosh, I might have to look this up a second. Oh, a and b are the x and y. So it's going to be x minus a plus b. I wish it was a different color to distinguish it from the background there. Let's go with blue to match the dot. There we go. So what happens is, as I move this dot, it's kind of cool. It is showing the tangent line of our function. Yeah, it's kind of like this. This is a nice way to verify our work with implicit derivatives and see if we kind of got a right answer. Certainly looks to be holding. It looks like a tangent line to me. And then, oh, are there areas where it's undefined? So we can see that as it approaches 0, it certainly looks like a vertical slope. So that makes sense. That's undefined. But what's going on with y equals x over 2? Let's investigate that a little more. There's my line y equals x over 2. As I move the blue dot, remember this is just an estimation of what's going on. Sure enough, there's a vertical tangent line, more or less, as I move along that dot. The weird thing is, I mean, the function itself is also undefined on a lot of these points. The only place where it's really like clearly defined is right there. I don't know if the x value is actually 2.5 or not. Maybe I could find the intersection. There we go, 2.5. So I don't actually know. That could be oversimplified rounding. I don't know what that point is exactly, and now I'm really curious. I think we're going to move on from the problem, though. If you wanted to figure out that exact intersection, you would set the line y equals x over 2. You would somehow figure out it would be a system of equations. When is this true as well as the original function? For what values of x and y are they both true? And you'd have to do a substitution. You'd replace y with x over 2 and then solve for this value of x. I think it's a cubic. So it'd be pretty interesting. If you want to go ahead and do that and let me know what the value of x is, that would be fun. You could show me your work. All right. So really fun to visualize that and see what's going on. Excellent implicit differentiation example there. I think we have time for one more question from 3.7. Anybody else? Yeah, Sharon. 62. Holy cameli, that makes me nervous. Getting up there in our numbers. Is it multiple choice? Oh, which of the following is equal to the derivative? Do they give the original function? Oh, okay, x squared minus xy plus y squared equals 1, which is definitely an ellipse. All right, x squared minus xy minus y squared equals 1. So Sharon, Can you let me know, how did you start this problem out?
So I got the first derivative right.
Oh, so you're kind of like 61, 62 sort of. Okay.
I got the first derivative, 2x plus y, divided by 2.
Can you say that one more time?
Negative 2x plus y divided by 2y minus x.
Okay. And I might just turn that numerator around to say y minus 2x. This helps me with my negatives to rewrite it that way. And I guess that would be letter what? A. Wonderful. So for 61, you find that option A is the answer, and Sharon shared her solution there. So let's go ahead and get to the heart of this question, which is with 62, where they want us to find the second derivative. Of course, the second derivative being the derivative of our first derivative. It's how it's always been, right? So in other words, I need to take dy dx equals y minus 2x over 2y minus x and differentiate it. It is a quotient, and we're not getting around this one. We're going to be using the quotient rule. I don't know why it keeps moving. Okay, there we go. So if I differentiate the left side, I get y double prime. I should probably switch to the prime notation. It's cleaner. So y double prime is equal to, and now I have to think about differentiating that right side. Okay. So, okay, it keeps moving on me. Sorry, if you could be patient for a second. I'll try and be patient for a second. There we go. So I get my quotient rule. Remember, if I'm taking the derivative with respect to x of, I think it's u on top, uv, that would be v times u prime minus u times v prime all over v squared. Very complicated. So this will be a little journey here. So here's my denominator, 2y minus x, times the derivative of my numerator, which would be y prime minus 2, minus my numerator, as is, times the derivative of my denominator, which is 2y times y prime minus 1. This is all over the quantity in my denominator, 2y minus x squared. And I'm going to peek at the answers for 62. Yeah, most of the answers in problem 62 for the multiple choice have the denominator in terms of the quantity 2y minus x. So I'm not going to expand it. I'm not going to square my denominator, which is often the case. We usually are just simplifying the numerator. In fact, for the sake of what I have to write, it's harder to write with this stylus. I'm not going to continuously copy the denominator. I'm just going to focus on, well, what if I simplified that numerator, and then we'll bring it all together. So if I just focus on just the numerator, here's what we get. I've got to double distribute, right, these products like so. So here we are. 2y times y prime minus 4y minus x times y prime plus 2x minus whatever I get when I double distribute the next two terms. So 2y squared y prime minus y minus 4x y prime plus 2x. All right, there's a lot going on there. Do I have any questions? Is there part of that we could look at again? Yeah, Adrian.
That's 2y minus y prime minus 1. And you get like I would understand you get the like y prime. I don't understand you get like this y and y.
Okay. I'm gonna have to look back and see why I did that. Because let's see there. I was differentiating the denominator. Oh no, I think you're onto something there, aren't you? Yeah. Yeah, it should just be 2. Absolutely. Absolutely. I have a mistake here. I'm so glad you caught this. Yeah, so let's see. Because what I want to kind of, pardon me, highlight for people at home so they can tell what's going on here. When I was differentiating that denominator to get like the v prime, what's at issue here is it should have just been, like Adrian's saying, it should have just been 2y prime minus 1 instead of 2y. So I'm going to go ahead and erase the y. There we go. Yes? Correct. Yes, correct. So that would change a little bit of our answer down here then, because there's going to be a factor of y that goes away in a couple of places. Let's see. So it would be, this would not be squared. And then this y would not be there. All right. Fantastic. Any other questions or concerns? Yeah. All right. I'm glad we caught it. Continuing to simplify our numerator, I'm going to distribute my negatives, so I get 2y times y prime minus 4y minus x times y prime plus 2x. By the way, none of these terms, these first 4 terms, are common. Then we have minus 2y times y prime plus, that's a y by itself. Yep, okay. Plus y plus 4x y prime minus 2x. All right, let's go on the hunt for like terms. I think there's at least some. So, oh, there's some like terms that actually end up canceling. Maybe I should start at the beginning of this expression though. We've got 2y y prime minus 2y y prime. Okay, those cancel. That's nice. What else? We've got some like terms here. I've got negative 4y and positive 1y there. So that would make negative 3y. Here's some terms with x and y prime only. So negative x, y prime, positive 4x. So that would be positive 3x, y prime when I combine them. Oh, and that's everything. So it simplifies to this. And then recall that y prime is, and I don't actually remember, so I got to go look, y minus 2x over 2y minus x. Y minus 2x over 2y, come on y, get in there, there we go, minus x. So with that being the case, I can back substitute, and I'm going to go ahead and bring my denominator back into this. So I think I'll go back to black here. There we go. So y double prime is equal to negative 3y plus 3x times y minus 2x over 2y minus x all over that denominator squared. Anybody remember that? What was it? 2y minus x, thank you. Okay. Wow. What a journey, and we're still on it. So from here, I think it would benefit us to get common denominators. I've got two terms in my numerator, so I'm going to multiply this term by 2y minus x over 2y minus x in order to get a common denominator. So I get negative 3y times 2y minus x over 2y minus x plus 3x times y minus 2x over 2y minus x. And this is all over the denominator, 2y minus x quantity squared. So you can see here that in my numerators, I have 2y minus x and I have 2y minus x in the respective denominators. So I can factor that out, and what that does is it creates like this. I can factor it out like this. I can put 2y minus x in front of this whole thing, and I get my denominator down there, 2y minus x cubed, squared. So you can see what will happen in the next line. Actually, let's just go ahead and keep going with just the denominator for a moment. What happens in the next line is we're going to get whatever our numerator simplifies to over 2y minus x to the third power when I multiply this 2x minus y times the 2y minus x quantity squared. So that's how our denominator will simplify. Focusing on the numerators, remember I factored out, let me get some highlighter here to make it really clear. I factored out that denominator with this term. So now I'm just left with the terms in the numerator. So I'm talking about these terms right there. So if I go ahead and multiply those out, what will I get? I'll get negative 6y squared plus 3xy plus 3xy minus 6x squared. Okay, and this is where we start looking to see how we could keep simplifying. I suppose that could become 9xy in the numerator. And so far, it doesn't match our answers, does it? So there's something in our work that's not correct. And I'm wondering if it's just a minus sign somewhere. I don't know. Anybody spot anything? This problem's very long, so it'd be nice if. So it should simplify to just 6, huh? Well, I'll be honest, I don't see it yet. We agreed, Sharon? Oh, Matt?
That's a good question. So like the green, when you switch to the green and black, why do you have to walk by
Y prime lived there. So whenever we want to find a second derivative, we often get y prime as part of the answer, which technically we don't want. So we have to back substitute and replace it. I'm looking for an error and I don't see it yet. Oh, wait a minute. What's going on here? Let's look at the original expression. Yeah, this is really powerful. Do you guys notice anything? X squared. No. Take a look at this. X squared minus. What is it? Not supposed to be minus? Oh, I want to cry. I wrote it down wrong. No, it will. I know what it is to wrap this problem up. I know what's going on. But seriously, I wrote it down wrong. Oh, but wait, Sharon, that doesn't change it because you told us the answer, right? Okay. But here's the deal. Do you notice that there's a 6 here? Happens to be negative. That's right. There's a 6 there. If I were to combine these, it would make 6xy, yeah? And there's a minus 6 there. Oh, this is so cool. This is so cool. If I go back to the original expression, if I multiply through by negative 6, negative 6x squared plus 6xy minus 6y squared must equal what? Negative 6, because I'm multiplying through by negative 6. So to finish this problem out, this entire numerator, oh dear, sorry to go back and forth like that. This entire numerator simplifies to negative 6, just like that. Just like that. So it's a second back substitution, which is really cool. This is the pinnacle of challenge for our chapter. There's no question. This level of work on an implicit differentiation problem is really fantastic. So that's an A-level problem right there for sure. Whew, I got excited. I like that. See, 62. You picked the hard one, Sharon. Okay. We got to go ahead and keep moving here, keep moving along. So, I'll try and leave more time for more questions in these sections. We're going to be reviewing content on Monday. You know, actually, I just made a decision. We're not going to cover 3.9. We'll get to 3.9 after the break. It's just too much, and I don't want to rush over much. So we're gonna kick off our review on Friday, and we're gonna have more review on Monday and Tuesday, and then we'll assess from 3.1 to 3.8 on Wednesday, Thursday. Blake? And not past the holiday, no. It just means that section 3.9 will not be on the exam, which is okay. It's okay. 3.9 is not anything huge, but I'd just rather not add more than we need to before the holiday. So let's go ahead and jump into 3.8. All right. So this is a exploration, but I'd like to do it together because there's not a ton of us here. So I think it's best if we just walk through it together. So if you could take a moment, this does need to go into your notes. So I suppose it will take a bit to write down. Or there's this video recording available too. So I'm going to double check that we're still recording. Make sure that I got video set up correctly. Yep, we're still recording. Good. Yep, correct. This is 3.8, which is the derivatives of inverse trigonometric functions. Of course, recall that we know the derivatives of the trig functions. We know the derivative of sine, cosine, cosecant, cotangent, tangent, secant. We know the derivatives for those. But there are times when we need to know the derivatives of their inverse equivalents. So here's a little exploration to get us started on that. So part A, if y equals the tangent of x, let's write this as an inverse. And we're not actually going to solve the inverse. we're just going to write it as an inverse. To do that, you switch your inputs and your outputs. So we have x is equal to the tangent of y. I have to be honest, this really bothered me when I first learned that in like algebra 2 is when we first saw inverse functions. And when I saw it in high school, I did not like switching the x and the y. And what I actually did was in my head, I just imagined I don't want x to be the input anymore. I want x to be my output. But for a lot of people, writing it that way is really helpful. So there's our inverse relationship. This is the opposite of y equals the tangent of x. It undoes y equals the tangent of x. It's true that in algebra 2 honors you would go a step further, of course. This would imply that y is equal to the tangent inverse of x. So that's kind of how this reconnects back to previous courses when we've worked with tangent inverse or sine inverse or cosine inverse. Most of the time, those were in problems where you were given an angle and you had to solve for a missing side. And cosine inverse or sine inverse were usually the tools to do that. Slightly different perspective here. So we're going to go through this exploration. We did step A. We found the inverse by switching our x and our y. And now we're going to differentiate both sides so that we can start to talk about, well, what's the derivative of this function? So if I differentiate the x with respect to x, I get 1. And on the right side, if I differentiate the tangent of y, recall that the derivative of the tangent of something is secant squared of that something. But like we've been practicing with the chain rule and implicit differentiation, I have to multiply by the derivative of that inside function, y, which is dy dx. Which is quite nice then, because I now know an expression for my derivative. The derivative of y with respect to x is 1 over the secant squared of y. That is a little bit scary though, because it's in terms of y, and that's harder to work with. So we're going to try and rewrite it so that it's in terms of x, and we're going to take away from this a formula for the derivative of tangent inverse of x. Blake? Yes, it would. Yes, it would. Recall that the trig functions represent ratios of the sides of a right triangle. In the triangle below, tangent of y is equal to x. Let's just verify that. Tangent of y, x over 1. So this triangle, the way they made this triangle is they put y as the angle right here. And sure enough, its opposite side divided by its adjacent side is equal to x, because this is x. It's kind of hard to see. That's x and that's 1. So that's what's true of our triangle. And I think Blank's right. It's probably easiest if we convert this to cosine squared of y. And now we're going to use our triangle to help define the cosine of y. To do that, I need to know this hypotenuse. Any ideas looking at this right triangle? How could I solve for the hypotenuse? Pythagorean theorem? Yeah. So Pythagorean theorem says one leg squared plus the other leg squared is equal to the hypotenuse squared. So if I think about it this way, it's going to be x squared and then also a 1. So it's going to be 1 plus x squared. That's the hypotenuse squared. So if I take the square root, that's the hypotenuse. The hypotenuse of that triangle is the square root of 1 plus x squared by the Pythagorean theorem. Pardon me. So part D says use the triangle ratios to find the cosine of y and or the secant of y. We're just going to stick with secant. With cosine. Cosine, if I stand here at angle y, that's supposed to be a stick man. It's harder to draw. Come on. So if that's my perspective at angle y, and cosine, of course, is adjacent over hypotenuse, so that would be 1 over the square root. Oh, come on, stylus, it's getting a little slow. 1 over the square root of 1 plus x squared. I'm going to minimize, sometimes this helps, just minimizing and opening the software again. The stylus is getting a little glitchy. All right, so now I have an expression for the cosine of y. The cosine of y is 1 over the square root of 1. Oh, come on, right. 1 over the square root of 1 plus x squared. That is not going to work. It's okay, we're almost there. So now could we make a substitution? If I take my expression for the cosine of y and I replace it over there, I can get dy dx in terms of just x. Oh, but it's becoming impossible to write. I might have to save this and then reopen it. Come on. Yeah, there's no other option here. So it's getting too glitchy. Smiles, you really have no idea why people aren't here today? Oh, okay. Huh? Yeah. No. I was just pulling his leg earlier. Wait, you still believe me? You thought it was okay. All right. All right, where do I want this thing? It's chapter 3. These are my brand spanking new notes for 3.8, which is derivatives of trigonometric functions. Mark 2. There we go. Let's see. All right, software is just being glitchy, so we're going to close it out and open it again. Hopefully, it'll run a bit smoother. Okay, my drive. Calculus. Chapter 3. 3.8. Derivatives of inverse trigonometric functions, Mark 2. It's going to take a minute to load. This reminds me so much, obviously, of remote learning. You guys weren't, none of you, of course, were in my class last year, but I was teaching out of a spare room that was a garage. And at one point, there was a windstorm, and this like 15-foot long tree branch comes crashing through my roof, and there's this hole. There was for a long time a hole in my ceiling with the branch sticking through in the background while I'm teaching here in remote learning. No, it didn't. No, it was like it happened. It was. I mean, it was a disaster. Yeah, that was fun. Okay, it's still taking time to load, which scares me. I think that it might still be super glitchy. Which I don't know why that would be. We got stuff to do. We got stuff to do. Come on, software. All right, so where we were before. We were going to make a substitution. I know that the derivative of y with respect to x is equal to cosine squared y. I'm just not satisfied with it being in terms of y. So instead, we drew this little right triangle, and we figured out that we can rewrite the cosine of y as 1 over the square root of 1 plus x squared. So what does that mean? It means that dy dx is equal to the cosine of y squared. So it's equal to that value squared. So I have 1 over the square root, oh, it's still a little glitchy, of 1 plus x squared, quantity squared. It's nice that we're squaring it because the square root goes away and I get 1 over 1 plus x squared. So to help you remember what's going on here, what is this result actually about? Let's go to the earlier part of the exploration. This is where we started, basically. We started with this relationship, and I want to remind you of the connection to that relationship then. If x is equal to the tangent of y, then by the definition of an inverse function, y is equal to tangent inverse of x. So therefore, what we really just found was a derivative. Oh, sad day. The derivative of the tangent inverse of x. All right, this is painful. Okay, so the derivative for the tangent inverse of x is 1 over 1 plus x squared. So make sure that if anything gets in your notes from this lesson, make sure you get that one. The derivative of the tangent inverse of x is 1 over the quantity 1 plus x squared. So we have a new tool now. We can differentiate things that have tangent inverse in them. And of course, you know what's next. The other ones. I think because of technical difficulties, I'm not going to try and film myself working through the other. There's some more investigations. We can do the similar thing for sine of x. It's a slightly different right triangle, but there it is. And we can do a similar thing for some of the other trig expressions. But ultimately, this is the master list right here. And notice that I'm not using x, I'm using u, because sometimes we have an inside function u. And by the chain rule, you end up getting u prime. If u happened to equal x, what would go on this numerator here? What would u prime be, Blake? It'd be 1. So like in the example we just came up with, the derivative with respect to x of tangent inverse of, if that were just an x, we would have just a 1, and that would be just an x. So this is sort of the simple form of the answer. But we know that it's not always the simple form. Sometimes the inside function is not just x. Sometimes the inside function is its own function that depends on x, like, x squared, or, something else. Do they? I'll let you in on a secret. I probably shouldn't. Most of the inverse trig functions that we refer back to for future problems in this class tend to be tangent inverse, because it's the easiest one, and sine inverse. Not to say that you could never see a cosecant or secant inverse problem outside of 3.8, but past 3.8, past chapter 3, the ones that actually come up in actual problems, especially problems that have applications, are tangent inverse, and then occasionally sine inverse. But there's all 6. Yeah. So your classmates are writing these down. If I had the patience for all the video editing, I would probably edit this out of the recording, but I think I'm probably just going to post it as it is. We've got a couple example problems that we're going to work through because we've done the exploration. We figured out why the answer for the derivative of tangent inverse of x is what it is. You could do a similar one for sine if you would like. It's prompted in the notes there. Here's all 6 of them. Obviously, you could like Google derivations for these. The text, as usual, has very little info. They do tangent. They show the derivation of the tangents. Oh, they do sine as well. And then the other ones they get from sine and from tangent, which is okay. All right, a lot to write down. So these will be posted to Canvas, both the video and the notes. So you can also copy down from Canvas there. Are we okay if I go ahead and go to the example problems? You can write these down from Canvas if necessary. Hopefully you already got a couple of them. Yeah, I could see how cosecant and secant both look a little like extra. Yeah. I guess one thing I'll point out while we're here is the use of the negatives kind of carries over from when we were doing this work with not the inverse functions, but just the original. So if there's a c, if it's a co of some kind, it is going to get the negative. So in that sense, if you were to like commit these to memory, you would really only need to memorize like 3 of them, and then just know that there's a relationship between cosecant and secant, a relationship between sine and cosine, and a relationship between tangent and cotangent. That's why they're named those ways. Basically, it's just that one is positive and the other is negative when you differentiate it. Those are the only differences. So it's kind of like 3 terms that you really would need to memorize. And I do suggest memorizing especially tangent inverse. That one will come up in future problems and in next semester as well. I mean, sine inverse could too, but it's mostly tangent that comes up. All right, so let's take a look at an example. What if we were to differentiate y equals a tangent inverse of 4x squared? I'd like to point out that this is not an implicit differentiation problem. Y has been isolated and written in terms of a function that is in terms of x. So we're back to an explicit differentiation problem. So let's go. I'm going to differentiate the left side, which gives me y prime, right? Just like we planned. Oh, I've got red. Okay. And that is equal to, and now we got to remember the formula. It's on we derived it earlier ourselves, and it's also on the previous page. So let's see. It's going to be u prime in the numerator, which would be 8x over 1 plus u squared. So the inside function 4x squared goes in there. Simplifying, I get 8x over 1 plus 16 x to the 4. So apparently that rational function is going to be the derivative of the tangent inverse of 4x squared. I'm tempted to put this on Desmos and graph it, but I think we're going to keep going here. Any questions to this example? Everybody map how it goes to the formula? Okay. Next, it says find the equation of the line tangent to. So we're going to find a tangent line. It's something that we bring up every single section. We're always finding the equations of tangent lines. It's never gone away. It's not going to go away. And this time it's for the function arc sine x. So what is that? I just need to remind you this is a notational thing. This means sine inverse of x. So all of the inverse functions could alternatively be written with arc, A-R-C. I don't know, it's notation. I think ARC is a lot easier to type back in the 90s when to the power of -1 was probably harder to type. So, well, yeah. So I think that's the reason why there's two different notations. And they come up all over, so you need to be aware of them. All right, so if I find the derivative, I can pretty much just write down the formula, right? So not that I remember it, it's u squared is positive, and it's u prime over the square root of 1 minus u squared, or is it u squared minus 1? 1 minus u squared. Excellent. All right. Now in this case, u is just x, and the derivative of x is just 1. So my numerator is 1, and I'm over the square root of 1 minus u squared. U is just x, so we have x squared. All right, so there's my y prime, the derivative of sine inverse of x, and they want us to find the tangent line. So recall that the slope of the tangent line is the derivative. Sorry. The slope of the tangent line is the derivative, at that point, x equals the square root of 3. So if I want to find the slope of the tangent line, I have to plug the square root of 3 over 2 into this expression here. So slope of the tangent line would be 1 over the square root of 1 minus the square root of 3 over 2 quantity squared. So then we get 1 over the square root of 1 minus, and I get 3 over 4. So 1 minus 3/4, which is 1/4. So I get 1 over the square root of 1/4. And this ends up being 2. But what I'm curious is, should we be considering plus or minus 2? And the answer would be obvious if we made a graph. And right now, just by looking at the algebra, I'm actually not too sure. Is it the plus or the minus 2? Thinking about the graph of sine inverse. Oh, that's what we should talk about. Let's briefly talk about the graph of sine inverse. So that's easiest to do. I keep clicking the wrong button. No, don't undo writing. If we first, there we go. If we first consider the graph of sine. So the sine curve, and I'm going to do this only for a very specific set of domain values. The sine curve looks like that. Okay. So there's sine. It has a period of 2 pi. So the inverse function is a reflection over the y equals x line. It looks like that. And technically, it's only defined on the domain from negative pi over 2 to pi over 2. Because if you go any further, it's undefined. And the square root of 3 over 2, I don't really know where it is, but I know that it's positive. So the square root of 3 over 2 is some x value that's going to live. Let's imagine that it lives right, I don't know, there. So if it lived right there, my tangent line is definitely going to have a positive slope. So by analyzing the graph, I can say I know with confidence that the tangent slope we're after is a slope of 2, not negative 2. Negative 2. Negative 2 would be extraneous. All right, so we found our slope. Next, I need to know what point the graph passes through. So to do that, I'm going to refer back to the original equation. So I guess I'll go with purple because purple represents the graph of sine inverse. So here we go. The output when x is the square root of 3 over 2 is the sine inverse of the square root of 3 over 2, which is what? Pi over what? You know this from your unit circle. Pi over 2 would be way up there, which sine of pi over 2 is 1. Pi over 4 would be the square root of 2 over 2. The sine of pi over 3 is 1/2. No, wait, you're right. The sine of pi over 6 is 1/2. The sine of pi over 3 is taller. I'll draw it. Right there. We're talking about this triangle right there. That's the angle. That's the one that has a y value. The x value is 1/2, and the y value is the square root of 3 over 2. And that angle measure is pi over 3 radians. So the sine inverse of the square root of 3 over 2 is pi over 3 radians. All right, so that's my output. The slope is 2, and the point that it travels through is the square root of 3 over 2, comma, y coordinate pi over 3. So let's write the equation to our line. We have y minus y1, so y minus the square root of 3 over 2. No, the output was pi over 3. So y minus pi over 3 is equal to my slope, 2, times the quantity x minus x1, which x was our input, square root of 3 over 2. And I'm not gonna simplify that to slope-intercept form. I'm gonna call it like it is. That is the equation of the tangent line for sine inverse of x when x is equal to the square root of 3 over 2. Let's verify that finding. We're gonna put this in Desmos and take a look. All right. So I'm gonna graph sine inverse of x. See, it's easier to type arcsine. I don't want to tell you, it's easier. And then I'm gonna graph what I hope is my tangent line. So y minus pi over 3 equals 2 times x minus the square root of 3 over 2. And that certainly looks tangent. So, I'll take it. Looks good to me. There we go. Sorry, question? Yeah, looks tangent enough. It's been certified tangent enough. So the assignment, I'll post the assignment shortly. And that's obviously this is something where you're going to want to work with your notes close at hand because there's a lot of formulas to write down. Also, I just hope everybody has a great day, and I look forward to more and more of you being back in my class. Let's not do this again. All right. Bye.